Welcome all to the decision analysis video lectures, and now we are in chapter 2, Eugene equally brisk synchronized rain gear. We solved the problem for Eugene already, and now in this section 2 we consider combining decision rules, also could be called as compromising. So what happened with Brianna and Eugene, that they chose different alternatives. And well, of course, nothing prevents them to use different gear when they walk to office and back. But let's see, for some reason they want to choose the same gear. So the problem is which gear to choose or how to find reasonable compromise. So there were just three alternatives. Let's just call them simply A1, A2 and A3 as they were. Brianna chose the alternative A2 and Eugene chose the alternative A3. And now, first, it might be reasonable to think that we now have to this A2 and A3 to choose in between, but this is not the way it should be analyzed, because it could very well be that A2 and A3 are very, in the sense that for Eugene, A2 is a horrible choice, and for Brianna, same, that A3 is a horrible choice. So could be that there is A1 is a nice compromise that are reasonable for both of them. Okay, this is possible. Let's see what happens, and let's see how we build this, combining these decision rules or compromising. So Brianna brisk and Eugene equally brisk both consider the subjective comfort. This is not important actually. They just had some decision matrices. What is important is their value functions. So how they valued each alternative. And this is indeed what we do. We base the compromise purely on the respective value functions. We now call them V of B for Brianna, V and V of E for Eugene. And all that we have to take care in order to combine these value functions in finding the so-called compromise value functions is that the V of B and V of E are the same type. By type I mean that they are both maximization or minimization. Let's assume always a type to be a maximization, and they are in the same scale. So otherwise it would be, so if they are measured differently on different scales, then the other one will get unequal or more weight than the other one, which is not what we want. And so first we transform both V of B and V of E to a maximization type. So let's see. So V of E, this is the Eugene's value function, this expected value, that's a maximization type already. So we want to maximize expected value. So there is nothing to transform here. However, the V of B, the Brianna's value function, is a regret type, which is a minimization type. So they want to minimize maximal regret. So it's a minimization. So the minimal value is chosen. So we have to change the minimization problem to a maximization problem. And how do we do that? Well, the transformation is simple. We just multiply everything by -1. So we transform it. Vi of B will be minus Vi of B. So after this, V of B is a maximization type. So that's simple. Then, which is slightly more complicated, we have to ensure that both V of B and V of E are at the same scale. And how do we do that? We affinely scale both of them. It means that we use, so here Vi is either both Vi of B and Vi of E. We do it for both. So the new Vi will be, I take the value of the unscaled value function and I subtract the minimal value, and then I divide it by this maximal value minus minimal value. So after this scale, all these Vi's will be on the interval 0 and 1 with the maximal value 1 and the minimal value of 0. It happens with this scaling automatically. And also we can do this so that we are not changing the preferences, meaning that if vi1 is less than or equal to vi2 before the affine transformation, the same is true after the affine transformation. It's a simple mathematical fact that you can see from this immediately if you think about it a little bit. So this is, whenever we combine decision rules, they have to be affinely scaled to interval 0, 1, and this is the scaling. Slight remark, so if this value function v is constant, meaning that the maximum and the minimum are the same, then we have a 0 divided by 0 problem. So how do we define 0 divided by 0? And in these notes we say that 0 divided by 0 is 1. This means that if the value function is constant, then we set v is equal to 1 for constant value functions. And here is a little bit of code. So in this course we will be using GNU Octave. I will later explain a little bit of it, but here is so-called scaling.m function file that does the scaling automatically. So this is something that we use in the code later on. So it does this transformation here, it happens here if we don't have constant value function. If it's a constant value function, it just returns once. But this is something that we just use in our codes. You don't have to understand how it works. It's not too complicated, but I will not explain it because it's only needed to know how to use it. You don't have to understand how it was built. And you can download this function from this web page, and you should download it and put it in your Octave working directory where you do your assignments. Okay, so let's get back to this combining these decision rules. So let's recall what is the regret matrix and the associated maximal regret values for Brianna. So this was the regret matrix. Again, now I'm using these abbreviations S1, S2, S3 and A1, A2, A3. And then the value of maximal regrets for Brianna 80, 20, 80. So what we pick up here is just the regret values, maximal regret values, or the value functions for Brianna. And for Eugene, if you remember, they were calculated like this. Now for Brianna, these are the minimization form. We make the maximization form. So we multiply that minus 1. And then we do the scaling. So here is the scaling for Brianna. So the value minus 80 here minus the minimum value, that is minus 80, and then the maximum minus minimum, which is minus 20 minus 80. So this is 0. V2, so minus 20 minus 80. So minus 80 was the minimal. Maximal is minus 20, so minus 20 minus the minimal minus 80, and this is 1, and the last value same way, that's 0. So the scaled value function on the maximization form for Brianna is for alternative 1 it's 0, for alternative 2 it's 1, and for alternative 3 it's 0. Let's do the same for Eugene. So for the first choice, first alternative, so that was 50, and minus the minimal is 0.25 divided by 70. 0.70, that's the maximal, minus 0.25, that's minimal, that's 0.56. Then the V2, similar calculation, it gives 0, and V3, so the alternative 3, it gives 1. Alright, so now we have everything we need for the compromise. So we have two value functions that are both the same type, maximization type, and they are on the same scale from 0 to 1. And we can consider the following table. So here we have, we don't have the scenarios anymore, we don't need them. And remember, the scenarios were different for Brianna and Eugene. So that was okay, that was no problem. What is important is alternatives are the same. So the alternatives, the values for Brianna are 0, 1, 0, and for Eugene 0.56, 0, 1. And now we have to combine these somehow. And how do we combine them? Well, we do a so-called convex combination. You don't have to remember the name convex. What you have to remember is the following formula. So now this is typical. So we call the V, and now parenthesis W. It means that we combine V of B and V of E so that V of B gets the weight W, so from interval 0 to 1, and the rest of the weight 1 minus W goes to E. So here is this. So Vi of W is W Vi of B plus 1 minus W Vi of E. And this means from that Brianna's point of view gets the weight W, and Eugene's point of view gets the complementary weight 1 minus W. And here we have calculated this compromise value function for different W's. So the weight is more or less a free parameter. It can be anything. Maybe the natural choice is 50-50. So both get the equal weight. But here, in any case, I have in this table, so here are the value functions, and here scale value functions, and here are the weights for W's 75%, 50%, and 25%, and you can see what are the values for different scenario, different alternatives. And for example, if we use this one, which is the natural one, so 50-50 weights for both Brianna and Eugene, then we see that the maximum is not unique. So A2 and A3 both get 50% of 0.5, and A1 0.28. So this means that alternatives A2 and A3 are equally optimal, and if on the other hand Brianna gets weight in the greater weight in the compromise, so we go to here, then the optimal is A2, and if we get bigger weight for Eugene, it is the A3 here. So that's the compromise solution. So if we have equal weight 50-50, then put A2 and A3. So how do they decide? Because they both are optimal. Well, natural way to do it is just to flip a coin, and then say head A2, tail A3. So that was all for this video lecture. See you in next video lectures. Bye.